Okay, let's talk a little bit about flip-flop and sequential circuit timing. So first, remember, sequential circuits are synchronized by having a clock signal, which is just a periodic signal that goes from being 1 for some amount of time, then going low for another amount of time. And usually it's about 50-50 the time it's high or low, but sometimes in some applications, we may have it be high less time than it's low. And so when we're talking about these types of periodic signals, we can also describe the duty cycle, which is just the fraction of the time that the signal is on over the clock period. And usually this is given as a percentage. So if I have a signal with a 10% duty cycle, it's going to be low most of the time versus a signal with a 90% duty cycle, which is high most of the time. Okay, so now let's talk about flip-flops, which are synchronous or edge-triggered devices. So they take our clock signal. And the flip-flop has some important timing constraints. So for the flip-flop inputs, in this case it's a D flip-flop, there's only a single input N. That input, and we'll say this is a positive edge-triggered flip-flop, there's some amount of time before the actual edge of the clock that the flip-flop input has to be stable, and this is called the setup time. Additionally, we also have some time after the clock edge that the flip-flop input in also has to be stable, and this is called the hold time. So what's going on here is that essentially, in order for this flip-flop to correctly read the input that I want to put into this flip-flop, it has to be stable T setup amount of time before the clock edge. And it also has to be stable and not changing T hold amount of time after the clock edge. Now, the flip-flop itself also has a propagation delay, just like we saw with combinational logic and gates. It's going to take some amount of time after the clock edge for my output to be stabilized and to see that change reflected. And so usually we call this the propagation delay of the flip-flop, or TP or TPD. Okay, so let's look at what this means in terms of a circuit and determining what's the worst case or the longest propagation delay to the circuit, which is important, as we know, for determining the maximum frequency which I can operate that sequential circuit. So let's say we have the following circuit. Okay, so there are multiple paths through this circuit. I have paths from the inputs to the flip-flop inputs, and that's going to happen in one clock period. I also have from the flip-flops to the output, also from the inputs to the output there's a path, and there's also a path from the flip-flop outputs back to the flip-flop inputs, right? And this is usually going to be our longest path, but let's put some numbers in here for our delays, for our gates and our flip-flops, and see what comes up. So let's say our gates all have delay of 5 nanoseconds. The flip-flop has a delay of 10 nanoseconds. The setup time is 3 nanoseconds, and the hold time is 2 nanoseconds. So going from a flip-flop edge to the next clock edge, and it could be from any of the flip-flops, but I'm going to go ahead and look at this one because this one feeds back into itself. I have to propagate through the flip-flop. That's 10 nanoseconds. Then I have an AND gate, which is 5 nanoseconds. And then I also have to have this signal be stable some amount of time before the clock edge. In this case, the setup time was 3 nanoseconds. So that delay from clock to clock is going to be 10 plus 5 plus 3. Now, usually also when designing sequential circuits, we include some margin or some buffer in that timing as well, given there can be variations because of temperature and other voltage fluctuations, to make sure that this flip-flop or register correctly reads the correct value. So say, for example, I had a 10% design margin. I want to add in a 10% buffer of time for this delay, so I'm going to multiply this times 1.1. This gives me a path of 19.8. Okay, just to be safe, I can check the other paths. So for example, input to the clock, to one of the flip-flop inputs. The longest path I have here, it looks like, is through one of my gates. And then, so I have a delay of 5, plus the setup time, plus my timing margin. So that gives me a delay of 8.8, which is less than the path from one flip-flop to another flip-flop, or from clock to clock. From the flip-flop, or the clock edge to the output, I have the flip-flop propagation delay, and then an OR gate, so I'm going to have 15 nanoseconds for that delay. Okay, so if I want to determine what's the frequency that I can operate this circuit, remember this is 1 over t, where t, this is the longest path through the circuit, or the worst case path through my circuit. In this case, it was 19.8. So 19.8 nanoseconds. So 1 over 19.8 nanoseconds is equal to about 50.5 megahertz.